So a quick video about going over the second worksheet I posted on Convergence series, so just some more practice. And so again, I'd recommend that you would, if you've already done the worksheet, great, then you could watch this to see how I did them. Of course, there are some of these, there's more than one way to do them, but at least you can check and see if what you're doing makes sense. So this first one, A, is I recognize right away that this thing is a geometric series in disguise. So I rewrite it as 1/2 so I can recognize the geometric series. Then I would say that this is convergent because it's a It's convergent because it's a geometric with r less than 1. In that case, that's all you have to say. So part B, or section B, whatever, this one is a little bit interesting. So as far as handling this thing underneath there, it's not a p-series, but it's like a p-series, so we'd use probably the limit comparison test here. And what I compare it to is b sub n equals 1 over n to the 3/4. And where I get the 3/4 is this is really like 1 over n times n to the 1/2, whole thing to the 1/2. So this inside would be n to the 3/2, and then that would make it n to the 3/4. So that's where that b sub n comes from. So then we take the limit. We put the limit comparison test up here so we know we're doing it. Take the limit of, as n approaches infinity, of 1 over the square root of n times the square root of n minus 1 times n to the 3/4 power. And of course, when n is approaching infinity, that 1 becomes insignificant, and this is really gets closer and closer to 1, meaning that minus 1 gets insignificant. So because we got the limit equal to 1, which is greater than 0, then we can say that, the summation of b sub n as n runs from 2 to infinity is convergent because p is less than 1. Whoops, sorry about that. It's divergent because p is less than 1. And therefore, the summation as n runs from 2 to infinity of 1 over the square root of n times the square root of n minus 1 is also divergent because we got a limit greater than 1 or greater than 0. That tells us that these two behave the same. Okay. This one is a classic ratio test because we got factorial and we have exponential. So I would say ratio up here just so I know which test I'm doing, and immediately go the limit as n approaches infinity of absolute value of 3 to the n over, 3 to the n plus 1 over 2n plus 2 factorial times 2n factorial over 3 to the n. And that's going to be equal to the 3n to the 1, the 3 to the n plus 1 and the 3 to the n cancel out, leaving just a 3 on top. And the factorials cancel out, leaving a 2n plus 2 times 2n plus 1. And so then we let n approach infinity, and we get this thing approaches 0, which is less than 1. Therefore, we can say that our original series converges because our ratio is less than 1. Okay, this one up here, part D, that's a pretty straightforward one. It is a geometric series, so we say that it converges because it's a geometric with absolute value, in this case, of r less than 1. That one's fairly easy. Okay, this looks like another, well, this looks like maybe, this one I think you could compare it, there's a couple different ways, but to me, I think it might be a good idea to talk about the absolute convergence of it. So if I take absolute convergence of this, that would be equal to the summation running from n cubed to n squared. And so then, if we can talk about just this guy for a minute, and we know that the limit of n cubed over n squared as n approaches infinity is infinity, which is not equal to 0. Therefore, this series diverges, which means, therefore, my original series, in running from 1 to infinity, of negative 1 to the n cubed over n squared. Oh, whoops. Yeah, I was going to use absolute convergence to prove this conversion. That doesn't work. Shoot. Okay, well, let's etch that one out. Because absolute convergence proves convergence, but absolute divergence doesn't prove anything. Okay, well. Okay, I'm going to try this again. We can just actually use the Nth Term Test directly from here. We don't need to go to convergence, or absolute convergence. So if we take the limit as n approaches infinity of negative 1 to the n times n cubed over n squared, that is actually equal to the limit as n approaches infinity of negative 1 to the n times n, because those n's will cancel out. And of course, that n is getting larger and larger, so it's going to hop back and forth between positive large and negative large. And positive large is definitely not approaching 0. So we would say not approaching 0. And since the limit is not approaching 0, then by the nth, by the nth term test, this thing diverges. And if we come over here, this one also diverges, but for a different reason. Well, actually, you could use the Nth Term Test there too, but this one diverges because it's geometric with r greater than 1. Okay, moving right along. Okay, this is a great one for alternating series test, I think. Let's use the alternating series test. So we pick our b sub n to be equal to 1 over the square root of n. And we show that that's positive. B sub n is positive. for all n greater than or equal to 1, and also b sub n is decreasing because n plus 1 is greater than square root of n. So that shows that it's decreasing. And then finally, the limit of, as n approaches infinity, of 1 over the square root of n is equal to 0. And so then, because we met the three conditions, this series, in running from 1 to infinity, of negative 1 to the n over the square root of n, converges. This looks like a great candidate for the nth root test. So we'll do the root test here. And so we would take the limit as n approaches infinity of this thing to the nth root. And of course the n's just cancel out, so I'm left with the limit as n approaches infinity of negative 2 over n, negative 2n over n plus 1. Whoops, I forgot, in the nth root test we actually take the absolute value on the inside of this thing. So on that so then that would not be negative there. So then as n approaches infinity, this thing is approaching 2, and that is greater than 1. Since the limit is greater than 1, let's check that real quick, make sure you see it. So notice that when it's greater than 1, then it says that it's divergent. The series is divergent. So we can go back here and we say, therefore, since we got a limit greater than 1, we know that this thing is divergent.
It is going very well.
All right, this one isn't jump out at us because there's no there's no factorial on this. It does have a negative down there, which means we can't use comparison test. Could use alternating series test possibly, but because there's power and exponentials mixed together, I think I'll use the ratio test. So we'll write ratio up here, and I'll take the limit as n approaches infinity, the absolute value here. That would be n plus 1 times pi to the n plus 1 over negative 3. If I put n plus 1 in there, that would just be n. And then we're going to divide that, which means we'll flip it over and multiply, so I'll have a negative 3 to the n minus 1 on top, and the n times pi to the n on the bottom. And so when we simplify things, that's going to leave me with an, well, that will cancel with that, leaving just a negative 3 on the bottom, and there'll be an n on the bottom, because those n and n plus 1s won't cancel. And then the pi to the n and the pi to the n plus 1 will cancel, leaving just a pi on top. So now when we take the integral, oh, and that's absolute value, so that'll take care of the negative. So we get the limit as n approaches infinity of pi n plus pi over 3n. And since pi is a little bit bigger than 3, this thing is going to be greater than 1. And since it's greater than 1, then we can say that this series diverges. Okay. Okay, finally J. This is not, because of the E in there, there is kind of an exponential power rule thing going there, but I don't know if that would help. It's not going to work very well with the ratio because we have an E to the N, so it's not, it's kind of like a P series, but it's not even an exponential because the E to the N cubed. So this one I think I would use the integral test. So we use the integral test. So remember that we take the limit as n approaches infinity of the integral from 1 to a. You really just take the integral from 1 to infinity, but that's an improper integral, so this is the way we do it. There should be an a there. Of n squared times e to the negative n cubed dn. Okay, so this is a fairly basic fairly basic u substitution problem to integrate. So I'm going to integrate that m limit as a approaches infinity. And if we let u equal negative n to the third, then du is negative 3n squared. So you can see that with the dn, of course, you can see that the dn and the n squared are pretty much that, except there's an extra negative 3 out there. So I'm just going to go ahead and integrate that. So it'd be negative 1/3 e to the negative n cubed. And we're evaluating that from 1 to a. Okay. So then we go ahead and plug that in. So the limit is still here as a approaches infinity. And that would be negative 1/3 e to the negative a cubed minus, which would be plus 1/3 e, and I put a 1 in there, and I just get negative 1. That's supposed to be an infinity there. And since that negative exponent pushes this to the bottom, so this is really negative 1 over all that stuff, so as a approaches infinity, this is going to be 0. So, and this just stays put, so we actually end up with an answer of 1 over 3e. And if we check real quick what that means with the integral test, the integral test says that, oh, we forgot to show that it's positive, decreasing, continuous. Whoops. But anyway, if it converges to anything, then the other one converges. So that was a bad example, sorry. But so this does converge. So then we just got to go back and show those conditions. So what were they again? I need to show that it's positives, decreasing, and continuous. So I actually really bummed this one. I should have picked an f of x first. So what I should have done is said, okay, f of x equals x squared times e to the negative x cubed, which is really the same thing as x squared over e to the x cubed. And then this all should have been x's up there. And then, so I'd show that that's always positive. So f of x is positive for all x greater than or equal to 1. And we know that's true because anything is always positive and something squared is always positive. Also, f of x is decreasing. How do we know it's decreasing? Well, we could take the derivative of that, which is not going to be pretty. Is there an easier way? Yeah, I think we'd have to take the derivative. So I'm going to go over here and say f prime of x is equal to 2x times e to the negative x cubed plus x squared times negative 3x squared times e to the negative x cubed. And of course, that's going to produce a negative number. This will always be positive. This will always be negative. And this is bigger than that. So let's see if we can show that clearly. So this would be 2x over e to the negative x cubed plus, actually minus 3x to the fourth over e to the x. Oh, what are you doing there, buddy? X cubed. Yeah, so we got 2x minus 3x to the fourth over e to the negative x cubed, and that will clearly be less than 0 for all x greater than or equal to 1. So we just showed us decreasing, and then finally we had to do this limit thing, if I remember right. Man, I'm forgetting this bad. Oh, show this continuous, right. And f of x is continuous. There are no holes or asymptotes or anything for all x greater than or equal to 1. And then we could say that with x's over you see a in, and then this would be a good. So then once we did that, we'd say because the limit converges, therefore the series converges. Okay, kind of bummed that one up, but you can ask me about that on Monday if you have some questions.